Hey everyone, in this video I want to go over this linearization problem, or also known as a linear approximation problem. So it says determine the linearization of the given function at the specified point, and then we're given a function and the point 0, 0 for part A, and then for part B it says use the linearization in A to approximate a function at another point, and it says to find the approximate value, not the exact value. So this is a problem that you would get in Calc 3. And before I go over how to solve the problem, I'm going to briefly explain what is linearization. So the main idea with linearization is, let's say you have some function, and at any point of the function, you can find the approximation of the function using tangent lines. So using a tangent line at this point, you would get the general slope of the function in this limited area. And also, if you think of a line as being a really zoomed in small portion of this function, the line will approximately follow the value of the function within a limited region. So if you find the tangent line over multiple points, you're going to approximate linearly what the function looks like. So the formula for finding the linear approximation at a point is going to be finding the tangent line at that point. In some cases, for functions at certain parts, for example, where there are sharp corners in a function or where the tangent line would be vertical, then you cannot find always the tangent line at every single point. And so in part B, that is referencing that type of problem where it might be difficult to calculate the linear approximation at a particular point, or it might just not be possible at certain points. And so what you can do is you can find it at a nearby point. So we're going to use the linear approximation at point 0, 0 to approximate the linear approximation or approximate the function at the point 0.1 and negative 0.05. So the formula for finding the linearization at a point, or the linear approximation, is really the formula for finding the tangent line at that point. And what that looks like is going to depend on how many dimensions you're working in. If you are in a single variable calculus class, the linearization will have the general formula L of x is equal to f of a, where a is the point that you would be given, plus f prime of a times x minus a. In our case, we are doing this as if it was a calculus 3 problem, so we're doing multivariable calculus, and we have two variables instead of one variable. So we have f of x and y instead of just x. And so we're going to need a more generalized formula for the linear approximation. And in this case, our formula is going to be the linearization of x comma y is equal to f of a comma b plus x minus a times f of x, which is the partial derivative of f in respect to x, of a comma b plus y minus b times the partial derivative f of y, a b. And so this is the formula we're going to use for part A. So for A, we're going to calculate A and B is the point that we're given, so A and B are both equal to 0. So for the first part, we're going to find f of 0, 0 by plugging into the function. So it's going to be 3 times 0 plus 2 over 2 times 0 minus 1. So it's going to be 2 divided by negative 1 is equal to negative 2. Next, we're going to find the partial derivative of x. So in the numerator, we're going to take the derivative of 3x plus 2, so with respect to x, that would give us 3, and we have as a constant 1 over 2y minus 1. So that's going to be 3 over 2y minus 1. And we're again going to want to plug in the value 0, 0. So plugging in 0 is going to give us negative 3. Then we want to find the partial derivative with respect to y. So that's going to give us a constant 3x plus 2. And 2y minus 1 in the denominator is equal to, this is equivalent to saying 2y minus 1 to the negative 1. So if we take the derivative of that, that's going to be negative 1 times 2y minus 1 to the negative 2 times 2. So that's going to be 2y minus 1 to the negative 2, which is equal to 1 over 2y minus 2 squared times negative 1 times 2. And again, we're going to want to plug in 0, 0 to that function, and that is going to give us negative 2 squared, which is equal to negative 4, over 0 minus 1 squared is 1, so that's negative 4. And now we have all the values ready to plug into our linear approximation formula. So the linearization of xy at point 0, 0 is going to be negative 2 plus x minus 0 times negative 3 plus y minus 0 times negative 4. So that's going to be equal to negative 2 minus 3x minus 4y. And that's the solution for part A. And then for part B, we're just going to use the solution that we found in A, so this formula, and we're just going to plug in the point 0.1 and negative 0.05. So we're just going to say the linear approximation of 0.1, negative 0.05 is equal to negative 2 minus 3 times 0.1 minus 4 times negative 0.05. And if we plug that into a calculator, that's going to give us negative 2.1. And we are done with this problem.